Another question that you might be confronted with in the homework, but I typically don't test on, is how many spanning trees does a graph have? And this is kind of like the question, well, if you're trying to find how many paths are between these points, how many circuits, it's not necessarily relevant for solving the problem, but it gives us a sense of how big of a problem is this and how many different answers might we be looking for. And that's a common theme throughout this book is when we're looking at a problem, how do we know how hard it's going to be? How many different actual possibilities do they have? And it's something that could be useful to really think about. But basically, the higher the redundancy, the more options for spanning trees you would have you would have an underlying graph. And so the issue here is that there's not like a simple mathematical formula for figuring out the number of spanning trees, but there are a couple tips and tricks. And there's a few things I wanted to, just tell you to help you figure out how many spanning trees you could have. But one way you could actually solve these sorts of questions is by literally like drawing every option you can think of, just through attrition by process of elimination. But there's a couple shortcuts, which is what I wanted to show you. So like let's look at one example of a graph which is not a tree, and we could talk about how many different spanning trees you could have. But remember that this graph is not a tree because, well, first of all, a tree cannot have any circuits. So in this graph, I can clearly see that there are two different circuits in this graph. Um, and basically this is preventing it from being a tree. Or another way, which is one of the ways I recommended before, is we could use the n-1 property to do this. Let me actually switch to the packet real quick. And we can, so that way I can write a little bit easier um, in order to address this question. But basically, in this graph, what we could first do is talk about how can we find a spanning tree, and then look at, well, how many different spanning trees would we actually have as a totally separate question. And, just to recap, in a graph, there should be every spanning tree should have n-1 edges within it, where n is the number of vertices. So in this graph right here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I'm going to go ahead and note that over here. N is equal to 13. And if we were to do n-1, that would of course be 12. Um, and so what that's implying is that in a spanning tree, we should have 12 edges. If this graph was minimally connected. And if we were to actually count up the actual number of edges, which we use m to describe, and well, at least the book does, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so our redundancy here is 2. And remember, to check the redundancy, just take the difference between how many edges it actually has versus how many edges it should have, or m minus n-1. And that would tell us, well, how many edges too many do we have? And that's something that we could kind of also see because notice that there were two distinct circuits in this graph. And each one of those is kind of not allowed. So we could kind of view that as, well, if I were to remove two of these edges, so just say use your imagination, say I were to remove, I think I can actually erase these. Let's say I were to remove this edge. Well, let me try to do this in a way that doesn't completely destroy the graph. It doesn't look like I can do it any finer than that. I think that's about as good as I can do with the tools at my disposal. Okay, and then I were to remove, let's just say, this edge over here. Cool, good enough. Now notice that this graph, there are no longer any circuits because I've broken them all apart. And once there are no circuits, your graph is a tree. Or again, I removed two edges because I knew that there was a redundancy of 2. And now this graph is a tree, it's minimally connected. Cool. So we would refer to this as a spanning tree of the other graph. And you could imagine a spanning tree by actually deleting edges, but usually what we do is we use highlighting as I did prior. I just would take highlight the particular edges that I'm focused on in the tree. And then that, I would just say that this is my spanning tree, and I'm imagining using those edges for my construction. But basically, if I was to know, well, how many different spanning trees would there be? Notice, like, that's the question I'm really wanted to focus on in this video. Basically, it's the process of removing edges from a circuit, and the number of ways that you could do that kind of influences the number of different spanning trees. Because all of those, like in a lot of these other edges, they were not composed of circuits. So these edges were all necessary for the connection of this graph, right? If I was to delete any one of those edges, that would create a disconnection no matter what. So those are like edges that I can't remove. But in the cases of where we have the circuits, those are the edges that I actually have options for. And those are going to influence how many spanning trees, how many different spanning trees the graph actually has. Because when I chose those two edges to delete, I picked them completely arbitrarily, and that would just give me one answer. But I could pick any one of those three or any one of these four, and no matter which choice I make, it would formulate a spanning tree. And actually, if you take the number of edges in the first circuit and multiply them by the number of edges in the second circuit here, this will give us the total number of spanning trees that this graph has, which is 12. And basically, this is a shortcut for finding the right answer. And now I want to say, well, why? This is actually what we call in math the fundamental counting principle, where if we have a set of choices where, in this circuit, we want to remove one of them to remove that redundancy, and we don't really necessarily know which one if we don't have the numbers to make that basis. Because if we're trying to find a minimum spanning tree or a maximum spanning tree, we would typically try to remove either the most expensive or the cheapest edge, depending on our goal. But if we don't have those numbers, well, we could choose any one of these edges because they're not weighted. And same with the second circuit over here, which has 4 edges. We could have made any one of these choices. So I have a set of conditions where I have 3 choices and a different set where I have 4 choices. If I want to know how many total different choices I have as a whole there, I just multiply the set of choices together, which gives me 12 unique options. Because basically I could remove this edge like I did, or any one of these 4. So you could imagine that, that would be one potential option for a spanning tree would be moving this one, or this one 2, or this one 3, or this one 4. So there's, 4 different spanning trees by keeping these 2 and removing any one of those 4. But also, I could have, instead of removing that first one on the left, I could have removed this one to start with and kept those other 2 right here and here, and then remove any of those 4. That would give me another 4 choices. Or I could have removed this edge, keeping the 2 at the bottom here and here, and removing any of those 4, depending on my choice, again, which would be 4 more. So 4 plus 4 plus 4 is 12, or basically if you just take 3 times 4, it gives us the total number of different ways to manufacture a spanning tree, and basically that would be an easier way to figure that out. But basically we could have done any one of those. And we can kind of imagine, okay, I'm going to use those 2. I'm going to use these 3. It doesn't really matter which ones I use. I'm just going to delete 2 in whatever configuration I want. And figuring out the number of edges within the underlying circuit is a shortcut. Now, when the graphs get more and more and more complicated, there is not necessarily, you can't apply this formula in such a simple way, because if you're looking at this graph, there's so many different circuits and they're overlapping circuits too, and the shortcut will not work anymore. But in the homework, if you are asked these questions, they'll be relatively simple, and you can use this trick to help you find the number of spanning trees. But the example from the packet just is to find a spanning tree for each of the following graphs. So in this one, let's just figure out one spanning tree, and we won't bother to figure out how many there are, because there would be so many for this one in particular. And that question does get harder and harder and harder the more edges you have and the more circuits that your graph contains. But anyways, so if we're starting, what I always suggest if you're trying to find a spanning tree is start by counting the number of vertices, because you're always going to have n minus 1 edges in your spanning trees. So I have 1, 2, 3, 4, 5, 6, 12, because those are both hexagons. So here we've got n is 12. And so n minus 1 is, of course, 11. So my spanning tree has got to have 11 edges in it. I could also figure out the redundancy here, but since, we don't really care about the number of spanning trees just because I didn't ask it. Basically, you could just connect, it's kind of playing connect the dots. You never want to build a connection that you don't really need. And with every choice, I'm trying to bring a new vertex into the network because we want to ensure that all of them are connected together, but we don't want to make any circuits as we're formulating a spanning tree. So every choice I'm making, I'm going to bring in a new vertex into my network. Um, and again, I'm choosing completely randomly. So here, and if I'm trying to figure out, well, how do I know when I'm done or how do I know when I'm stopping? I'm trying to use 11 edges, so I could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I notice I'm not done. Well, and another way I can figure that out is, well, F is still not in the network. And again, I could connect F however I wanted to, like that, or whatever. But basically, once all the vertices are connected, and assuming that I have used the minimal number of edges, that's a spanning tree. And again, just one of many, many different examples. Um, and also, one thing you might be wondering is one of the conditions of a tree is it's not allowed to have circuits. But sometimes when you're formulating spanning tree, like if you look at right here where I'm circling, it might appear to have a circuit and it might be a little bit confusing, like is this a circuit or not? But remember the thing I addressed this I think back in chapter 5 is that when there's not a vertex for overlapping lines, this does not count as a circuit because this is not a turn. This is not a location for where power could be rerouted. Even though if you're thinking about building power lines, right? If we're building power lines crossing over each other, you would think that there would be a place where you could actually connect them there. Um, and it's formulating a circuit. So technically, this could be visualized as not minimum because of this circuit. But when we're actually constructing a graph, overlapping power lines, when you have one line on top of another, if there is no vertex, that means that they are not actually connected. So what you could have is that the lines overlap geographically, but don't actually intersect for whatever reason. Or, I mean, again, these graphs don't necessarily have to be geographically accurate. While it looks like they are crossing, they might not actually be crossing in real life. But this obviously adds complexity to the problem. So in a real problem, we might just want to put vertices here and here, but you notice that it would change the problem because those aren't necessarily towns that we're trying to route power through. But I think you can see that these problems could become a little bit more complicated depending on the circumstance and when we do have overlap. But in general, what our graphs tend to look like when we're doing these sorts of problems is they tend to not have overlapping edges like that because at the end of the day, we're trying to build power lines between different cities. It doesn't necessarily make sense to build really long ones, say, for example, going from V to T, overlapping all the other options. And usually we just think about what are the nearest geographical neighbors and how much would it cost between just those pairs.